Good afternoon, everyone. This is Chelsea from ICEAA, welcoming you to another of ICEAA's Technology Showcase webinars, where the providers of the tools that make your jobs easier get to show off the latest and greatest of their products. Today's webinar is sponsored by Palisade, and we'll be learning more about using their at-risk software. I'd like to welcome Dr. Steve Van Drew, who is giving his fourth Tech Showcase webinar presentation, modeling OLS-based CER errors. Steve?
Thank you. Thanks for sharing your lunchtime if you're on the East Coast, or late morning if you're somewhere more in the middle of the country or out west. The topic for today, as Chelsea read, come on, now my slides don't want to advance. There we go. Modeling OLS-based CER errors sounds like a bunch of alphabet soup. OLS, ordinary least squares, and CER, cost estimating relationships, which probably doesn't need to be spelled out for this community of cost estimators, but I didn't want all of that spelled out in the title, or it would have just kind of overwhelmed the website. I do want to make very clear, though, that the focus here is on OLS-based CERs. I'm not going to be getting into MUPI or any of the others that do anything other than the calculus-based ordinary least squares approach. And I recognize that kind of puts us in an elementary position, and that's on purpose. I think in order to understand any of the advanced regression techniques, it's worthwhile to go back and look at some of the fundamentals of the original form of regression, ordinary least squares. So that's my purpose, and I wanted just to set the expectations by telling you that. Here's what I plan on covering in our 45 minutes to an hour together. Going over the regression fundamentals, the assumptions involved in ordinary least squares. Hopefully got some Power Excel users in the room, but even the people who've used it for a while may not be aware of all the functions and the tool that's available in Excel. So I wanted to cover that first. Then I wanted to do a demonstration using Excel's regression analysis capability of a linear CER. And then, since Palisade is hosting this, is paying for this, I wanted to show how to use their add-in, simulation add-in to Excel to implement an at-risk version of the linear CER. In other words, how do we include that error term from the cost estimating relationship when it's just a linear-based regression model? Then I want to cover some of the fundamentals of the nonlinear, specifically the two intrinsically linear regressions, the power and exponential models. Briefly talk about the transformations involved to get to those, and then focus on the error term that comes out of that approach to regression, which ends up being multiplicative log normal, as opposed to what you'll find out in the ordinary least squares. Linear is additive and normal. So linear, additive, and normal. Nonlinear, these two intrinsically linears are going to have multiplicative log normal error terms. And so I want to demonstrate that as well, specifically for the power form of the intrinsically linear model, show how to implement that in at-risk as well. So that's the plan. Here are the fundamentals that I've kind of alluded to. I'm going to show you and work with an equation, although people write this all kinds of ways. Here's the form of the equation I'm going to work with, where A is the y-intercept, B is the slope, and that epsilon at the end, you see it's an additive error term, errors, residuals, synonymous for this application. The assumptions, the specific assumptions that are necessary for the calculus behind ordinary least squares to work are that error term is normally distributed, that it has a mean of 0, that it has a constant variance, and the individual errors or residuals are independent of each other. Those assumptions are necessary to get us to the point where the equations I'm sure you've all worked with before allow us to estimate an intercept and a slope so that we can build the equation. I had to do it with a calculator, it's been so long, but just before coming live, I was curious to see how long ago it really was since I was first exposed to this. And I'm not ashamed, I'm kind of proud actually to admit that 45 years ago is the best I can pin it down. Spring 45 years ago, I think is best I can pin down when I saw my undergraduate prob and stats class. And the reason I'm bringing that up is I still remember very clearly, because for whatever reason it was pretty profound to me, and I've learned a lot more about it since, but I still remember the day at the blackboard. Yes, I learned with blackboards and slide rules even. But I remember the professor standing up in the problem stats class and showing us an equation like or exactly like this, and then lining out the epsilon and saying essentially, and I'm sure I'm paraphrasing, but saying we can ignore this error term because on average it's 0. And then he proceeded from there, and we never came back to talk about the error term. And so if you read the description that I gave for this webinar, I really want to go back and clear up things that weren't made clear enough to me, at least 45 years ago. And that's what do you do if you want to include the error term or feel that it's important to do that? That's what I want to expose you to today. And specifically, I want to show you how if you're building an overall cost risk, cost uncertainty analysis model, that you can use that risk to do that, including an objective-based input model for the error term around the regression that takes advantage of the assumptions that have been made all along. They're always there, it's just we seem to ignore them. And in the description for this webinar, I said that on average, that's a safe assumption with the linear model, because on average, the mean is 0. But those of you in this business, cost estimating, know that we really don't have a chance for most of our applications of regression to find out what happens on average. We get a one shot at it typically. One program that's approved, one time that this regression is being used to estimate some cost element. The error term never has a chance to come back to its mean of 0. So knowing what its full spread can be and seeing how that relates to the other risks and uncertainties in a model is an important thing to do, as opposed to just assuming that on average it's 0, so let's ignore it. So I kind of want to peel back the onion on that and show you how to get to it. It may not seem that dramatic for a linear model. On average, it's 0. When we get to the power model in particular that I'm going to demonstrate, with the data set I'm showing, you're going to see that ignoring that error term puts you 27% low with your unadjusted, unerror term accounted for estimates. And so it becomes even more significant when you're working with the nonlinear models. And that's something, if you've never seen that before, I hope really jumps out at you in this presentation. So let's go to work from there. If you're an Excel user, you may know this already, but the difference between functions and a tool in Excel is that the functions in Excel, and I've listed 4 of them here that all would help with regression, they are dynamic. So if you use in a cell, if you say equals intercept and you give the range of the y's, the range of the x's, and hit return, it'll give you an estimate for the intercept for the data sets that you've provided. If you go in and change any data point in there, that function, because it's dynamic, it's live, it updates automatically. And all 4 of these functions are like that. So if all you're interested in is solving for the intercept or the slope, or if you want to just jump ahead and say, I know what my x is going to be when I use this, here's the y's, here's the x's, here's the x I'm planning on to use it for, you can get a forecast and be done with it and never see any of the statistical considerations that go along with it, never see anything about the error term, and just get an estimate that projects it like regression would do for you for a specific value of x. That's taken a lot of shortcuts that I don't necessarily agree with. What I tend to do, but it does have one drawback, I tend to use the data analysis regression tool instead. And as a tool in Excel, it is static. The results from it are static. It provides a table of the statistical characteristics of the regression fit. You go back and change the x's and change the y's, your regression table from this tool doesn't update automatically. So that's kind of a useful difference to know about. And I know that not everybody who works in Excel is even aware of the difference. I like to see the additional stuff that comes out of this regression table, p-values and things like that. So I tend to use it, but I may also at times include some of these functions off to the side just so that I can, once I've seen the quality of the regression, if I have minor changes in the data set, I can go in and see immediately how those impact the estimates for intercept and slope. Just something to make you aware of. I'm going to be using for sure this regression tool in the demonstration. And if you've never seen it, it's you have to add it in. It comes with Excel. You just have to know to add in the 2 data analysis tool packs. And once you've done that, on the data ribbon in the data analysis dialog box, you'll have a choice for regression. And I'll demonstrate that shortly. So here's the data set I'm going to work with. Let's imagine 10 systems, and I think in the original problem I took this for, these were radios. Not that it really matters, but dollars and thousands for the cost. You see that they range from a cost of 1.6 thousand up to 22.2, and then beside it you see the weight in pounds for those 10 systems. Off to the right you see an XY scatter that shows the 10 systems costs along with their weights, and you can see there does seem to be a slight upward trend, which is trying to suggest to us that as weight goes up, cost goes up, which most people would know for electronic systems seems a little counterintuitive, but that's what the data is showing us. I'm also not blind. Anybody can see that that's an outlier up there, but I've left it in, which is going to cause the error term here, as well as some of the statistics, to not be very good, but I know it's there, and I would not stop with this, but it's what I'm using for an example. You know, there's all kinds of ways of demonstrating that's an outlier, and then going back and refitting it. Take that data point out, you lose a degree of freedom, which is going to impact our fit statistics. So you have to do that consciously, but I consciously, and for this demonstration, chose to leave that point in. You probably know that if you in Excel you've done an XY scatter plot, all you have to do is right click towards the center of the data, and you're provided with options that allow you to plot the trend line, which is shown here. It shows an R squared and it shows the equation. So this is all being done in a chart though. I can't access these values out of the chart without going back and using one of the functions that I've shown you here. But it's useful to kind of see that right up front. Terrible R squared, I admit that, but I know that if I stick with the ordinary least squares approach to regression, in this case, a linear model is going to have an intercept of 2.48 and a slope of 0.08. Okay. And the X's that we're working with should, which are the pounds, should range between 24 and looks like 161 is the maximum. So as long as we're sticking with weights that are between 24 and 161, then whatever we determine about the fit of this model would apply. We wouldn't be extrapolating to go below 24 or above 161 if we stick in that range. So you can see pretty quickly that there's the fit, not a great one, but there it is as a line, there's its R squared. If instead, and I'll jump out and show you this live in a moment, but here's a screen capture of what the regression tool in Excel would do for you. And I've highlighted the colors here for a few things because it's going to help us navigate around this result. This is what the regression looks like the tool provides. You see some of the same things we saw a moment ago. Buried down here in the lower left are the values for the intercept and the slope. They are, and I'll jump back to the previous slide, they're the same thing that we saw when the equation was printed in the XY scatter. Mean of 2.48, 0.083 for the slope. I think I said mean a minute ago, I meant y-intercept. There they are, y-intercept and the slope. So those are the two coefficients. They are in cells now, which means that I can reference those and build equations off of them when I go to do more with this model. Some other things that show up, if you're familiar with doing slope coefficient tests, then the 0.083, that's the slope here, if we were to do a full-blown hypothesis test on this, and had we used a level of significance of 0.1 or 10%, we actually would have concluded that the slope is statistically significant because the p-value is 0.085. So we're somewhere between a 0.05 and a 0.1, depending on which of those level of significance you'd used would determine whether you'd classify the slope as being statistically significant or not. You see the R squared in kind of that magenta color up here. And then if you've never focused much on it before, I want you to notice that the standard error, 5.808, and then down here, the mean squared residual, mean squared error. If you were to take the square root of 33.7283, you would get 5.807. In other words, that mean squared residual, MSR, MSE, if you want to call the error instead of residual, the root mean squared error is in fact the standard error. That's significant for what I'm demonstrating here because that becomes your estimate of the standard deviation for the regression's error term. So in this form of the output, all you do is grab that standard error, and that's what you work with for an additive normal error term. It's in a cell so you can access it and anything I want to do later. So you can put all of that together. We have an intercept plus the slope times the weight. We already talked about the weight being in the relevant range. What's not on here, because I haven't talked about at risk yet, is how to capture that error term that has a mean of 0, and this is its standard deviation and is normally distributed. Some of you would take the next step, even without at risk or any of the other simulation add-ins, and would at least take the prediction interval approach. And I am using prediction here instead of a confidence interval. Prediction because we're talking about using the equation for a single observation out of the range. So this is wider than a confidence interval would be. So this is what you would use if you were planning on using the regression equation for a single value of X, substituting in the equation, what's your prediction for that value of X? And you can see the range here is pretty wide, and it does go out and grab that outlier. That's got a lot to do with how wide it is. You probably also are noticing that a whole lot of the lower portion of that interval drops below 0, which for the cost of a system is an absurd result. But that's just another way of kind of pointing out to us how terrible this model is, or said differently, how important it is to model the error term along with the prediction by itself. Sure, I could grab X, substitute X in the equation, and get a value off of this line, and everything would look like it's hunky-dory. The prediction interval here, which is capturing 90%, is telling me there's a whole bunch of the time where you're below 0. So these are absurd results. And the values are so high up, plus this is just a 90% interval. So there's still a 5% chance of being above or being below those values. Okay? But it's a handy thing to have done, and I'll include that in my demonstration shortly. So they're using the T distribution because of the sample size is the formula used to get a prediction interval here. If I wanted to implement this in at-risk, which is a simulation add-in, what I would do, and I'll show you this live in a moment, the whole thing, but I'm taking the intercept plus the slope times the weight I want to use, and then I'm adding another term, which is that error term we've talked about. The error term is normally distributed with a mean of 0, and that value right there, just as a reminder, is coming from the output back here as that standard error, or the square root of the mean squared residual. So the root mean squared error, the standard error, is my estimate for the standard deviation of a normally distributed error term with a mean of 0. And it's important to note, because it'll be different shortly, that with this linear model, it's an additive normal error term. So real quickly, what I'm going to show you live in a moment, so you can kind of navigate around it, I'm going to use a value for weight of 80, which is close to the center of gravity. I think it might even be right near the mean of the x's. I'm going to show that when the mean of the error term is 0, that our point estimate, if you will, is 9.13. And I'll kind of grade out in this section of the spreadsheet. You can see that I've also calculated the prediction interval, the lower and the upper level of that. And then I have this term that if you've never worked in at-risk, you'll see how to implement. I have in cell C34 a normally distributed input to this simulation with a mean of 0 and a standard deviation that's coming in from J9 in my particular case. And what you can see through this dialog box is all the statistics off to the side, and this is an at-risk dialog box. You can see that the min is negative infinity, positive infinity for the max because it's the normal distribution. Mean, mode, median, all of 0. And there's the standard deviation we specified. And so when this is live, I can take the handles in here, type in numbers for the different amounts, slide them one way or another, and kind of check out what the probability is of being at or below certain points. This is a dialog box showing that I've specified for the cell that I'm pointing to in that case, in C34, a normally distributed error term, mean is 0, and the standard deviation coming in from cell J9. And I'm going to tell you, and I've already kind of warned you about this, that the cost, because the prediction interval is showing it, sure enough, even for a weight of 80, which pushes us out about halfway into that regression, even at that much of a weight, about 6% of the simulated costs come in less than 0. So we'd have to have some kind of plan for what to do with those, maybe a filter that discards them or something along those lines. So let me leave the PowerPoint for a moment and take you into the spreadsheet. And Chelsea said this, Megan provided just before we came live, provided a way of getting the files and so that you can look yourselves. And if you haven't seen that in the chat, chat session, she gave a link that takes you to the TechShowcase area where both of these files are included, my PowerPoint and my Excel file. You're looking at the at-risk ribbon right here. And with the at-risk ribbon, you see a bunch of red and blues. And if you've never worked with at-risk before, I'm going to talk to a couple of these fairly quickly. But just to help you navigate through it, upper left corner is the data set that I've already provided you with. I've got, because I need it for individual calculations to come up with the prediction intervals, off to the side in column E, I've done some X times X and some products of X and some other things that I needed to work with the prediction interval. You see in this section, the summary output piece here, including residuals, everything kind of in columns I through Q. That area was generated by the Excel data analysis regression tool. It's the same one I had a screen capture of in PowerPoint, except I didn't show the residuals there. I just showed the upper portion and talked you through why I highlighted the things that I did. Here's the model, though, that I want to talk you through. This is what at-risk can provide for you. Down in this section, what I've done is, first of all, I'm implementing I'm telling, I've got to have it typed somewhere. I'm typing in that I want to use a weight of 80 pounds for X. Then what I'm doing is, in this lower section, in cell C35, you can see in the formula bar, don't pay attention to the risk output piece yet, but you can see, double click it so you can see it light up, that I'm pulling in the intercept and the weight from the regression results. I'm multiplying that slope times the weight of 80 pounds. So all I've done in this section right here is with the weight of 80, multiplied it by the slope, added it to the intercept, and that, when the error term is 0, is telling me that I've got a point estimate, a predicted value for a weight of 80 of $9.13 thousand. Okay, and that's as far as many of you would have taken it. Some of you might also have gone in and said, well, for that weight, what's our prediction interval? And I've got those highlighted off to the side. I made kind of grayed out, but I've calculated the range of that. And it's quite a range, minus $2.2 thousand up to $20.45 thousand. Notice that we are going below 0 there. And then our point estimate, 9.13. The thing that at-risk can add that takes you beyond just coming up with a single predicted value and maybe calculating the interval is actually turning this into an input to it, ultimately to a full-blown simulation. I'm treating this cell right here, this normal, and you can see in C34 that it says in the syntax, risk normal, mean of 0, standard deviation is the next piece of the syntax, and it's pulling that in from J9, and then I consciously decided to call that the linear error. I mean, I put a name there so in all the graphs and statistical summaries it would have that name included. If you have not seen at-risk do this, it was as simple as going to the distribution button on the at-risk ribbon, and in this version, which is 8.1 now of at-risk, had I wanted to do something different, there are 81 different distributions available to me. I chose normal, and it needs a mean and a standard deviation, which I can give it as cell addresses, and you see that I've done that for the standard deviation. There's me putting a name in there, and then a statistical summary off to the side. That's all I've done, is inserted that into a cell. That cell then is included in the next cell. It's adding then in that error term also. Well, it's still 9.13 right now because the mean of the normal is 0. With the at-risk ribbon though, there's a spot right here that I'm pointing at. Hopefully my cursor is showing you. Up about halfway through that at-risk ribbon is a die, a single die. If I click on that, then notice that in cell C34, the value in there now is a 2.1. In fact, if I reach up and hit F9 on my calculator, that value cycles through some positive and negative values. Every time I hit F9, function F9 on my laptop, I am resampling from that normal distribution. And if I wanted to keep track of those, they better be normally distributed with a mean of 0 and a standard deviation of what I told it to be. Take the dice back off, the die back off, it goes back to the static value for that input distribution, which is 0. Okay, so the idea of the simulation running is as many iterations as I tell it to run, it'll be sampling from that normal. It's always going to have 9.13 as the predicted value, but then the error term will be flopping all over the place with a mean of 0 and be normally distributed with the correct standard deviation. So if I've got downstream calculations that are using that cost for that radio, maybe it's just one component of a larger product that's being manufactured, then you'd want this same kind of treatment for all the different cost elements that have regression behind them, plus maybe some data fits for other uncertainties and maybe some risk register inputs to your cost estimate. So this is just one small piece of what you might be doing, but all it takes is letting the at-risk during the simulation randomly sample from that normal error term. If I simulate this alone, which is a very straightforward model, one input, one output, I want to show you what we'll get. Right now I've got it set up to run for 5,000 iterations. I'm going to, well, I've already run it to tell you the truth, so I'm not going to waste your time showing you that. If I go in and explore the results for this run so far, here's what we get coming out of cell C35. The simulation results for 5,000 iterations for the cost of an 80-pound radio tell us that sure enough, the mean is going to be that 9.1, call it 3. So it didn't change the mean any, but it's given us this entire spread, including, if I make this a 0, you can see that I said about 6%, and that's what happens. 6% of the iterations resulted in a cost that was less than 0. You want to pick something, some other value in here. Maybe you were budgeted to a certain amount. Call it, we'll call it 13,000. Well, you've got a little under a 75% chance of the cost for that radio coming in at or below 13,000. So the live results give you the ability to do all of this. I could also go in and generate some reports pretty quickly. Could generate a report. One of my favorites is this one called compact output, and I can tell it that I want to put it in the active workbook, generate the report, and it slaps it onto a tab here with some information, the statistical summary. And even people without or at risk will be able to see the PDF, see all the statistical summaries. This doesn't mean a whole lot because we only had one input, but if we'd had multiple inputs, then this would be providing us with a rack and stack view of the ones that have the largest impact on the variability of that total cost. So this is an example of what one type of report that can come out of at risk. That was all for the linear model. Megan, Chelsea, this might be a good time before I transition to the other type of model to see if there were any questions. I've been kind of watching chat, and it doesn't look like I've seen any questions yet. But maybe they're not being passed on to me.
Nope. It looks like there's no questions so far.
Okay, good. I'm going to jump on over to the power portion of the presentation then. So I'm going back to my PowerPoint. So we've covered all of this, showing you how to implement in at risk, an additive normal error term. Everything comes out of the regression output. Now let's talk about the nonlinear, or what are better referred to as intrinsically linear models. Here on the left of this chart, you see the linear model that we just talked about, a plus b times x, the y-intercept a, the slope b. A power model, and this is just one form of it, but the power model might look like a times x raised to the b, so we'd have to estimate a and b, which is an exponent in this case. The exponential model, a times e raised to the b times x, same thing, you'd have to estimate the a and the b. These on the surface look like they're going to be nonlinear models, and they are, but through appropriate transformations, we can take them from being nonlinear equations into what I've heard people refer to as intrinsically linear. So for the power model, if you do a log-log transform on both the y and the x, you end up taking that curve and turning it into a line. The intercept is the natural log of a, the slope is still b. Instead of working directly with x's and y's, you work with the natural log of x, and it provides you with an estimate for the natural log of y. So we've gone from this nonlinear equation to, son of a gun, out jumps a linear equation. And in this case, what we would be solving for, the intercept is the natural log of a, where that line crosses the y-axis, and the slope b. With the exponential model, transforming here to get to an intrinsically linear, you leave the x's alone and just do a log transform on the y's. That gets you to this particular graph, natural log y versus x, which provides you with a linear form for an equation. We'd have to estimate the natural log of a, estimate b, work with x's directly, untransformed, and end up with the resulting natural log of y. So I've seen some places refer to these two lower graphs as being in fit space, and all the ones in the upper area are in unit space. So the important point here is if you're doing power and exponential modeling, it can be much easier, since you're working with linear models in these cases, to do the appropriate transformations and do exactly what I just finished showing you in fit space. And the key that's not on this chart is if you're working with the linear forms of these two, the linear form of the power, the linear form of the exponential, or the linear itself, in all three of those cases, you have an additive normal error term. The trick is, and I'm going to say this a couple of times and demonstrate it, the trick is what is additive and normal for these two lower intrinsically linear equations become multiplicative and log normal in the upper two power model forms. So it's kind of a choice. Do you want to work with everything down here in fit space where it's aligned and it's additive normal, and then kind of as a last step, transform the result back to the unit space? Or would you rather just solve for it this way and then plug them in there and then work with a multiplicative log normal back here and over here? That's going to be your call. I'll show you that in at risk, there's a real simple distribution choice that can help out with that. But I'll say it again, it's really your choice. So let me show you for a power model a little bit clearer maybe what we've just said. With the power model, which for those of you that may not be aware, the power model gets used a lot because it's a learning curve model. It's the model typically used for learning curves. So while we're on it, paid political announcement, the 28th of April, I'll be back with the ICEAA Technology Showcase again, doing a lot data-based approach to unit learning curve models. So this is, although it's not a prerequisite in a strict sense, it will help having seen this for the 28th of April's presentation by ICEAA. So about a little over a month from now, I'll be drilling down and going into detail on one of these demonstrations for a unit learning curve model coming from lot data, which is calculationally, it's got a couple little tricks to it, including using goal seek. But what we're going to do right here is stick with the basics. You see the power model in what people refer to as unit space. You see it as a nonlinear model there. And if I've drawn this at all well, you can see that that obviously is not a normal error term around it. It is a log normal error term. So you can see that the tail of it extends to the right, which is on the high side in terms of Y. So there's more errors. The errors above are where we're really at risk there, if you want to think of it that way. You do the transformation, you're working with natural log of Y, natural log of X. You have additive normal error terms now. Okay, so you see an additive epsilon there, error term. Over here, that is actually a multiplicative error term. Here it's normal, here it's log normal. And that's what this bumper sticker that I've got in kind of light blue calls out. So here we are demonstrating that. And that's what can, for some people, make this a little challenging, although it's not that bad if you sit down and go and try it. If you have a normally distributed error, if you have something normally distributed in as a variable y, and raise that variable e to that variable's power, you end up with a log normal distribution. Okay. So what throws us off here, and this is really something you're going to have to think about and get your brain around, but play with the numbers a little bit, and you will see that not only are we throwing off it being additive and normal versus multiplicative and log normal, but we're also messing with the idea that that normal had a mean of 0. I wish it was as easy as saying, you know, e to the 0 is a 1, so your mean of the log normal is going to be 1, but that's not true. This is really a bizarre feature, but the additive normal error term in intrinsically linear regression space, fit space if you will, becomes multiplicative, it becomes log normal, and its median is 1, not its mean. Its median is 1. Its mean ends up actually being larger than 1. How much depends on that standard error, the estimate from the normal distribution. And if you want to physically calculate what that's going to be, then the equations are here for the mean and the variance. Or, and that's what you'd need to use if you had only some way of generating log normal error terms. At risk, the people who developed this must have seen enough applications like this to recognize, let's not bother having to go through all of that nonsense to calculate the mean and the variance. Let's just take the mean and the standard deviation from what the normal was, and at risk does the work in the background, but calls it a risk log norm 2 distribution instead. This is significantly easier to work with. You can always do this, but if you do, you're going to have to go through the calculation that I'm showing above for the mean and the variance. And for most inputs, the syntax, and that's why I've got the 0.5 exponent here. So usually you want the standard deviation, so you'd have to take the square root of that. And I'll demonstrate this in a moment. And the numbers that are going to come out to play are, for our example, are the ones showing here. And what I really wanted to demonstrate before we got too deep into the details of this is if I use what's known as log norm 2, so you can see it here, my mouse, I'm kind of circling the risk distribution on the left. It's a log norm 2. To get that to work, I'm telling it a mean of 0 and a standard deviation of 0.6917, which you'll see in a moment comes from our standard error out of the regression output for the intrinsically linear fit. If I'd wanted to instead, I could have jumped in and told it to model a log norm instead of log norm 2. But notice them somewhere I would have to have made the calculations that I'm showing you in the graph in the call out box above. This is what you get. I've got a backup slide that shows the calculation of that. But if you had taken the mean of 0, standard deviation of 0.6917, processed those through these two calculations, you'd end up with 1.2703 and 0.995. Those are the actual parameters for the log norm. And notice, please, that over here in the right side, that's exactly what this log norm's true mean and standard deviation are. But all of that work was done in the background for us if you use the log norm 2. Don't know how to say it any differently to make it clearer, but it's a nice thing for at-risk to have done for us, is to provide us with this, save us the burden of having to go through those calculations. Everything's done in the background. So, and the two are equivalent. The distributions are equivalent. That's what I'm showing here in this call out at the bottom of it. So, a little bit different data set now, and this is part of that spreadsheet that you have access to also. Same 10 systems, same 10 costs, but now instead of the weights in pounds, I've got a column, another X that I'm working with, which is the power out in watts. So 10 different of those. You see it looks like the minimum is a 0.5. You see the maximum here is 400. So quite a spread for watts. You see a lot of it concentrated in down below, at and below 100, and then one way out at 400 by itself. You also see one up in the $20-some thousand range, which potentially I could almost guarantee that one on the at 400 is an outlier. That one may be as well. I've left them in just for demonstration purposes, but were I to run this for real, I would want to investigate, first of all, see whether they're outliers and see what the effect is on the fit statistics of tossing one or both of those points out. With them included, I've taken, like my previous slides showed to do, I've taken the natural log of all the costs, the natural log of the watts, and what you've done by doing that is, instead of this kind of positive bend thing like that, maybe for a power model, we've got in magenta in an intrinsically linear fit. I didn't call out the equation there, but I will show you the full-blown effect of that with the regression tool. But you can see the natural log of power, natural log of cost. You can see some down below zero even. There's 2 points down there. It goes along with this one here. And you can see that there is definitely a line that's been fit to those points. And it doesn't appear to be that bad, but those outliers might have had a big impact on it. Here's the regression output from Excel. This is still just Excel, and hopefully you've kind of gotten comfortable now with the layout of this. That's the data set I showed a moment ago. What we're out to do is working with the natural log of the X's and natural log of the Y's to do a linear fit. So this is a linear fit to the transformed variables, and it's telling us that the y-intercept is 0.95, that the slope of this in its intrinsically linear form is a 0.35, call it 3519. You can see that the significance, the p-value here are both telling us that had we done a test of this, that the slope coefficient would be statistically significant at an alpha of 0.05. Even though its R squared is pretty poor. The other thing you can see here is this standard error, root mean squared error again. You see it coming out at that point. You see it, the square root of this would give us that. So either place you want to go, just recognize here you'd have to take its square root first, but you're being provided with the additive normal error terms standard deviation, but it's in fit spaced. So let's look at how this all gets played out to put an equation together. It's telling us that for the natural log of A, which is from this coefficient section, the natural log of A is the intercept. But if you go back to these slides here, it's this formula that we're working with. We're working with in the transformed fit space model. We've solved for the intercept as the natural log of A, and we're solving for B directly. The slope will be direct. And then we have to work transformed X, transformed Y. So going back to the output from that, natural log of A is what I'm provided here as the intercept. B is what I'm being provided with as the slope. Now I could, to solve for A, if I want to write it as the full power model, you just raise this e to that power and you end up with 2.5892. So remembering that, now I've got a natural log of A, I've got a B, and I've got A itself. I'm prepared to write the equation either way I want to do it. I could either write it in fit space as intercept plus slope times the X variable, which happens to be the natural log of power out here, or I could write it as a power function. And the power function there is A times X raised to the B. You see the A, that's why I showed you how to solve for A. 2.5892 times whatever X we want to work with, raised to the 0.3519 would directly give us the cost in thousands of dollars, an estimate of it for that power. If I use the first form of the equation, which is the linear form, I have to work with the natural log of the power, multiply it by the slope, add it to the intercept, And then I still would have another step to take because this is the natural log of the cost in thousands of dollars. I'd have to raise E to this results in order to turn it into the actual cost. So there's movement back and forth in these between fit and unit space. Got to keep clear of which one you're working with. What I haven't put on this slide, and what we're going to have to figure out how to implement in that risk, is if you work with the first form of the equation, which is the intrinsically linear form, then you're going to have an additive normal error term like we did in the previous example. If instead you want to work with the power form of the model, then you're going to have to work with a multiplicative log normal error term. You'll get the same results. That doesn't matter. So it's really more a matter of personal preference, which is the more intuitive way for you to do it. Here's what it looks like when I get into Excel. I've chosen in this particular case to go ahead and work with the power model itself. So I'm working with, and I'm going with a 60 watt system being estimated. So I'm taking the 60 watts, substituting it into the equation, raising it to 0.3519, multiplying that by that value of A we found. And then to do a full implementation, I have to work with a log normal distribution of the error terms. If I work with log norm 2, notice that 2 there in this, if I work with that form of it, it has a mean of 0 and a 0.6917. That comes from this cell, the standard error out of the regression output, 0.6917. If instead of using a 0 and a 0.6917, I had felt okay going through these equations up here on the top of this slide, then I could have used the log norm form and substituted in 1.2703.995. Okay. I chose to go with log norm 2. It's easier for me to work with, but I wanted to demonstrate to you while we're here, and you got a slide to show it, that yes, when you work with log norm 2 and give it a 0 and that standard error from the normally distributed error term in fit space, sure enough, over here on the side, you end up with the appropriate mean and standard deviation. And there's the mean, and down here's the standard deviation. Okay. The most significant thing of this part of this to me is I never really appreciated, and probably because it was 0, never really appreciated with linear models ignoring the error term because it had a mean of 0. Okay, if I use it over and over and over again, then all right, on average the error is 0, so I feel fairly comfortable ignoring it. Here's what happens though with the power model. In this particular case, if you ignore the error term, then you are ignoring being 27% on average low with your prediction. So that's the significance of going from fit space back to unit space with a power model. With any kind of significant standard error from that fit space, you're talking about a very biased estimate, 27% low on average right out of the gate with this particular model. And that sounds pretty extreme, and I can tell you from working cost estimating for quite a few years, that in maybe more typical applications, I would not be surprised to see something even as much as 10% usually show up for learning curve kind of applications of this. So that's not very good when your point estimate on average is 10% even low even. In this case, it's 27% low. So let's jump over to back into the spreadsheet. I'll show you the implementation of this live, and then I'll take some questions if you've got any. Got a different tab here. Notice how in this case that I have taken the time for the system to do the transformations up here. They were in dollars and thousands and watts down here. I've taken the natural log of the table above, basically. So you can see that every one of these X's, every one of these Y's has had their natural logs taken. The fit that I did, this regression output corresponds to the transformed variables, not the untransformed. This is a linear model now. The linear model is giving us this as an intercept, which is the natural log of A. It's giving us this as the slope, which is which is B itself, no transformation needed. You see, like I showed you before, that we were significant at an alpha of 5%. And this standard error is the important piece to work with for what I'm going to show you next. So down in this section of the model, I'm saying if we had power out of 60 watts, and that is within the original range, remember it was 0.5 to 400, so we're okay there, no extrapolation. Then I'm showing that the equation for Y, I did have to raise EXP. I had to use the exponentiation function to do this, but I pulled the two coefficients in. I've pulled the original X in as a straight weight, didn't have to do any transformation of that. And then I'm multiplying it by C33, which is where I'm going to put the error term. So with the dice off, we're looking at 1.27 as the average for that log normal distribution. So it's taking all what is happening already is an adjustment, and I put it over grayed out on the side. If I don't include that 1.27 multiplier factor, my initial estimate prediction would have been $10.94 in thousands. If I wanted to know the mean of coming out of that, then I'd have to apply that 1.27% factor, kicks it up to $13.89 in thousands. And that's before I do any simulation. This is just going in and modifying the point estimate to account for the average multiplicative error of 27%. So if a multiplier of 1.27 kicks me up from that unadjusted to this adjusted estimate. When I put the die on, you can see the impact of this log normal function input error term is going to take us all over the place from 0, which is the lower endpoint of the log normal, up to positive infinity unless I truncate it somehow. So the values there are what we're interested in doing with this, is running a simulation where my error term is, I use the log norm 2 version, mean of 0 and a standard deviation coming out of J9 here, which is that standard error. I'm using that as a multiplier on my estimate and watching what happens in cell C34. I've run a simulation already of C34, so I can go in and browse the results. And you can see here that sure enough, that's going to take on its own kind of log normal shape. You can see that the mean is 13.89, and I should get that if I go back and take the die off. 13.89 is the mean of the simulation results. You can see I've got a min down at 0.697. Those are dollars and thousands. A max all the way up about 141. And then all the statistical information you want in between. So if we went to 10.94, which is what my point estimate would be without any consideration for that error term, you can see that that 10.9 is the median actually, not the mean. That's because the multiplier being a 1 comes from the mean having been a 0 in fit space. Translates to a median of 1 in unit space. So only 50% of the time you are at or below your unadjusted. 50% of the time you're above it, but the mean got pulled in the direction of the tail, which is where I've been reporting that 1.27, 27% effect from. Hopefully I've explained all that well. Just to kind of summarize again, the things that I've said multiple times that are worth repeating here. If you're doing linear regression, ordinary least squared, cost estimating relationships, please don't forget that you have an additive normal error term. It's a real easy matter to find the standard deviation for that. From regression, it's the standard error. The regression statistics provide you that as the standard error. When you go to one of the intrinsically linear models, in fit space, you're still doing linear modeling. In fit space, the error terms are still additive and normal. But back in unit space, both the power and the exponential models have, as I've just finished demonstrating, a log normal error term. And the average here can put your estimates biased, as this example showed, right out of the gates. On average, you're 27% low in this particular data set, and it was for a model that had a statistically significant slope. So at risk makes it easier to implement because of its log norm 2 function. I would expect those of you that do cost risk, cost uncertainty analyses to see that that this is really just one input to what can be a whole lot more uncertainty and risk treatment in a model. Don't forget that if you're doing regression analysis, you have objective-based inputs to your analysis depending on the error terms for the regression models. Megan, Chelsea, that's all I'd planned on covering. I know I haven't left us too long, but I can see the chat. Doesn't look like there's any questions yet. So
we do have one question from Jay Black.
Jay Black, how are you, Jay?
Hey, Steve, how you doing? Well,
man, it's been what, 15, if not more years? How are you, sir?
Yeah. Doing good. Always like seeing an elegant presentation here. So thank you.
Elegant. Okay, I'll take that.
All right. Yeah, you had a question. Earlier in the presentation, you had, you were touching on the prediction interval, right. And of course, you had a plot of the prediction interval, and it does cover a wide range, kind of above and below, that trend line. I was just curious, you were walking through, which error term to use, to plug in to at risk. In these examples, were you plugging in the standard error, or were you calculating the prediction interval and then using the prediction interval?
No, I used the standard error. I just showed the prediction interval kind of as a progression. Somebody who wasn't going to do at risk or any simulation could at least have done the prediction interval. I did not use that anywhere when I ended up running the simulation, except just kind of as a benchmark to show. No, I didn't even use it for that, to show how often it went below zero. So
okay, yeah,
I used the standard error, not the interval.
Yeah, I remember. Gosh, in fact, back in 2014, now Dr. Christian Smart and Mark Greenberg, I think he was at NASA at the time, gave a presentation about risk modeling, and we're really championing the use of prediction intervals because, like you'd illustrated, they cover a little bit wider range than just the standard error. They had presented this lengthy presentation that kind of left me scratching my head, and then I went back to my desk at NAVC at the time, and I was asking myself, well, how do I actually model a prediction interval? So I put together a little ICEAA brief. I presented essentially just, how to model prediction interval using at risk. And I did that in 2017, a few years back now. I noticed that kind of in the intervening time, the, user interface, has changed. It's been updated, looks a lot sleeker in at risk now versus, where it did, roughly 5 years ago. I was just curious if I could just touch base with you offline, just share you that brief presentation I put together. And if you think that still accurately allows me to model a prediction interval, using that risk.
Yeah, I'd love to see that, Jay. Thank you. I'll get from either Megan or Chelsea. They've probably got your.
Okay. And I believe that it's publicly available. The title of the presentation is just what did I call it? I called it, modeling prediction intervals. Using Monte Carlo simulation. I think if you even just stick it into Google, with ICEAA, like the presentation is publicly available.
Okay.
Like for anyone on the call that's just curious, what do I need to do to model that kind of long, complex looking prediction interval equation? Boy, that looks difficult. I'm not sure I got the time to do that. I just, like I said, put together a quick presentation that just kind of outlines, that actually it's not really that difficult. You just plug a few things into Excel and that gives you what you need to plug into at risk. And
so then, when you did that, I'm guessing you probably used, because of our business, you probably had smaller data sets, so you were using the T distribution?
Yeah, I used student T.
Okay.
And then, but really kind of rubber hits the road is, when you sometimes sit in these presentations and you're looking at that prediction interval equation, it's like, boy, that looks like there's a lot of stuff there. Yeah, I know, I understand kind of the sales point, as an analyst that, that helps me model a wide risk range, but I've got, 50 other things I got to do to get my estimate out the door. I'm not sure I got time to really get in the weeds on this guy.
My question would be, if you do go past that point, if you want to do anything with it, are you working with those interval values then? So you only really are taking the point off the line or curve itself, and then the upper and the lower points for any given X. So you've got 3 possible values you could work with. What I like about this approach is you've got an infinite number of them. which then allows us to, if it's appropriate, like it probably will be, to introduce correlation later. I don't know how you would do with that with a prediction interval approach. This would allow me in a full-blown risk analysis to include correlation in here.
Yeah, I know we kind of ran out of time here. That is a consideration. I was hoping to, get your kind of read on what I shared a few years ago, but kind of one of my punchlines from the brief just at the very end was that, if you use the prediction interval, then I was able to kind of pump up the CV, that slope of the CDF to a double digit number. If I use standard error, it was like a single digit on kind of a, example regression. I've used the prediction interval, then I get like a double digit CV. And oftentimes, back in those days, again, this is a few years ago, there's a lot of interest from our senior leaders in having a larger CV versus a smaller one. And the prediction interval let me achieve that.
Absolutely. Well, I have to look at your paper, Jay. I appreciate you bringing that up.
Yeah.
And, actually, you guys can search for Jay's paper on the ICEAA archives page. So that's easily accessible to everyone.
Cool. You still with NAVC, Jay?
No, I work with HHS now. Yeah, developing software of all things.
Okay.
Yeah.
Cool.
All right, guys, we're just about out of time here. We're gonna wrap this up, if that's okay.
Sure.
Like Steve mentioned earlier, he will be back next month with another presentation called Modeling Unit Learning Curves from Lot Data. You guys can see that on the ICEAA Tech Showcase website. And Steve, if you have any closing remarks you'd like to make?
No, just thank you again for joining me in this COVID lunchtime.
All right. Thanks, everyone, and have a great afternoon.